A company with a cost and revenue function increases their production from x equals 100 to x equals 110. We're going to assume that x represents the number of items they're producing. We're supposed to use a differential to approximate the change in profit. So a differential is when you're talking about the dx and dy terms here. So in this case, we're talking about the differential to approximate the change in profit. So we want the change in profit with respect to the number of items they produce. So the change in profit divided by the change in the number of items they produce. Okay. So in order to do that, to find dp with respect to x, we need to know what p is. Whoops. We don't have a profit function yet, but we can get that real quick. Profit is just revenue minus expenses, right? How much money you bring in subtracted by how much it costs to make that stuff. So the profit function is going to be 5,050 minus x squared. And then look, I'm going to protect this in parentheses. The entire cost needs to be subtracted. If you were to just put the minus sign without the parentheses, you'd only be subtracting the first term. Okay, so simplifying a bit, 5,050 minus 2,050, that's 3,000. And then we have a minus x squared, and then minus a negative 2x. Distribute that negative sign. That's a plus 2x. There's our profit function. And now let's do the calculus part. The derivative of the profit with respect to time. The change in the profit, with respect to the number of items produced. So we need dp dx. So if you take a derivative of this with respect to x, the derivative of 3,000 is 0, right? Because the rate of change of a constant is 0. The derivative of negative x squared is negative 2x. And the derivative of 2x is just 2. So there's the rate of change of the profit with respect to the number of items produced. Okay, so we don't have a number here. We don't know, we haven't approximated the change in profit. But that's what they want you to do with this dx part. This is the change in profit with respect to the number of items produced. They went from 100 to 110, so that's a positive change. That's an increase of 10 items. That's what dx is, right? Dx is the rate of change. The rate of change starting here and ending here is a positive 10. If it went the other way around, if it started here and went here, then we'd say it went down, so negative 10 for dx. But that's what it's saying, is to plug in 10 in for dx. And the last part we're missing is a number for x, so we're starting at 100, right? You know, when you calculate a percentage, it's always the amount of change divided by the amount you started with. So it's a similar idea here. When you're trying to find out the change in profit, we start at 100, so we're going to plug in 100 in for x. And then if we solve that, we get dp over 10 equals negative 200. Here, I'll finish that. Negative 200 plus 2 is negative 198. If you multiply 10 to both sides, then the change in profit is negative 1,980. So it's gone down. Supposed to find dv if the sides of the cube change from 8 to... Okay, so we need a volume. A volume of a cube is just s cubed, right? Because volume is length times width times height. If you're talking about a cube, looks like this. That's my cube, right? And it's length times width times height for volume. But it's a cube, so all these are the same. They're all s. Okay, so this is our formula for the volume of a cube. We want to know what dv is. So if you take a derivative with respect to the side length, then you're calculating this, the derivative of the volume with respect to the side length. And that's, if you take a derivative of this with respect to s, it's like this is your x variable that we usually use. The 3 comes down, gets reduced by 1. So there's the derivative with respect to s of this relation. Okay, and now we can start plugging in our differential information. ds, the side length, the sides change from 8 to 8.2, so that's a change, a positive 0.2 because we went up. If the side length went down, then we put in negative 0.2, but it started here, ended here. And remember, we plug in the starting amount in for our variable, so it started at 8. And then if we're trying to get dv by itself, 8 squared is 64. 64 times 3 is 192. And then we want to multiply 0.2 to both sides to finish solving. So it looks like 38.4 is our approximation. We're asked to estimate the change in the surface area. So a lot of these problems, actually they usually use A for surface area. A lot of them you'll have to, if you don't know them, you have to look up these formulas to begin with. Surface area of a sphere is 4 pi r squared. Okay, so they want to estimate dA, and then it's with respect to the radius, because the radius is changing from 3 to 3.1, so the radius is the thing that's changing. So if I take a derivative with respect to the radius of the entire equation, this is what the derivative with respect to radius is symbolized on the left side. And the derivative over here, we've done this before with x most of the time. And then now we can plug in our differential information. We increase by 0.1, so 0.1 goes on bottom. And then over here, the starting radius was 3, so we plug that in. Oh, I didn't even read the whole problem. Look, it tells you the surface area, sorry. Okay, and then to finish solving that, dA, do they want it in terms of pi? No, they want in decimals. So that's 24 pi, but if I multiply by 0.1, that's 2.4 pi. So 2.4 times 3.1416. So 7.5 is to the nearest tenth.